Welcome to this lecture. This is the fourth lecture of week 5. We have discussed about the convergences of random variables. Now we are going to talk about certain specific properties related to the distribution of random variables, and this takes us into the discussions involving characteristic functions of random variables. Recall that in our basic probability theory discussions, we read about moment generating functions and the characteristic functions. There we are essentially looking at the Laplace transform and the Fourier transform involving the underlying distributions. Presently we are discussing everything in the measure theoretic setup. So we now revisit the discussions involving the characteristic functions involving the measure theoretic setting only, and we are going to define the characteristic functions purely using the measure theoretic setup. Without further delay, let us continue the discussion using the slides. So we are going to discuss these characteristic functions corresponding to probability measures as well as the setting of random variables or random vectors. Remember, we are always going to write RVs to denote random variables, but whenever we are talking about random vectors, we will explicitly mention that. Now here, if we consider these random variables or random vectors, that will be considered on a specific probability space, but if we change this setting, then we will mention this from time to time. Alright. So before we make the definition of a characteristic function, we recall some very basic facts about complex numbers. The fact is that if I take a real number x, then exponential ix is actually given by cos x plus I times sin x, and here the modulus of exponential ix, that is this exact quantity which always turns out to be 1 no matter is the value of small x. Now note that if I am interested in the real part of this complex number and the imaginary part, then the modulus of them is exactly modulus of cos x as well as modulus of sin x. But then individually these real parts and imaginary part, if I look at the modulus of that, that will be dominated from above by the modulus of exponential ix, and therefore this quantity is always equal to 1. So there is a minor correction here, this should be equal to 1, and this is true for all values of small x. So therefore this real part as well as the imaginary part, which are actually given by cosine of x and the sine of x, they are always bounded between -1 and +1. Now we also recall another fact that we are always going to work with the setting of real lines or RNs with the Borel sigma field, and whatever probability measures we are going to consider on, let us say, Rn will be considered to be Borel probability measures, meaning they are defined on exactly on this measurable space. Alright. So now let us come to the definition. So we take any probability measure on Rn and define the characteristic function corresponding to that. So let mu be such a probability measure. Now we are going to look at the corresponding Fourier transform, which we first denote by mu hat in this way. So this is the function defined like this, that I take any vector u on Rn, then for any such u I will look at the mu hat of u defined by this integration of exponential of I inner product between u and x, and that integration is with respect to the underlying probability measure, and this integration is being performed over the whole of Rn. But now if I split the real part and imaginary part of this complex number inside the integrand, I will essentially end up with two integrations here. So there is a I coming up here. Remember, I denotes the square root of -1. Alright. So therefore mu hat for every vector small u is given by this addition of these two integrals. Now here the important notational convention is this: this inner product is actually the standard inner product on Rn. This is also written as u transpose x, and that is exactly the component wise terms like this, u1 x1 plus u2 x2 up to un xn. Sometimes we also refer to it as the dot product on Rn. But now recall that the cosine and the sine functions are always dominated from above by 1, and therefore what we end up having is that these two integrands that we are using in our computation above, they are bounded whenever I fix a vector u in Rn, and therefore their integrals with respect to probability measures always exist. Alright, so we are just using the fact that if I have a bounded measurable function, here I have a nice continuous function, so that is also measurable. So for any bounded continuous function, their integral with respect to the probability measures always exist, and therefore the Fourier transform that we have defined is existing for all possible values of u, and therefore it exists on the whole of Rn. So there is no problem in making this definition. So just to compare, in the moment generating function setting, we have to be careful about using the Laplace transforms. There are many examples of random variables and their corresponding distributions where the moment generating function may not exist, but in the setting of characteristic functions, we always have that the characteristic function exists, and we have ensured that that exists simply by using the fact that for any bounded measurable function, the integration with respect to any probability measure always exists. So here we have applied that fact to these very specific continuous functions which are bounded and continuous, and therefore we have the existence of the corresponding Fourier transform. Alright. So now what we are going to do is to actually change a notation from this mu hat to phi subscript mu. So this is what will be our notation for the characteristic function corresponding to the probability measure mu. Now in dimension 1, let us just rewrite the expressions once more just to increase our familiarity with these expressions. So we are looking at this characteristic function. So for any u on the real line now in the one dimension, we are just integrating the function exponential iux with respect to the measure mu. Alright. Now exponential iux, as pointed out earlier, it just splits into the cosine and sines, and that is exactly what the characteristic function corresponding to the measure mu looks like. Alright. Now this is important to note that if I take any n-dimensional random vector x on some probability space omega fp, then we have mentioned earlier that we can look at the push forward of the measure p, which is given by p compose x inverse, that is the induced measure on Rn. Alright, and this turns out to be a probability measure, and this is what we refer to as the law or distribution of this random vector. Alright, so again, whenever we are talking everything in terms of random vector in the n dimensional setting, if I take n to be 1, that is the one dimensional setting, all these statements applies to the case of random variables. Alright, so we are making statements for any general dimension n. So let us now make a definition for characteristic functions corresponding to any random vector. So what we will do is that if we have a random vector defined on some n dimensional setting, then the law is exactly given by this p compose x inverse, and what we are going to do is to look at the characteristic function corresponding to that law, and this is the function we will refer to as the characteristic function of x. So from x I look at the law, and corresponding to the law I look at the characteristic function, and that characteristic function is what I refer to as the characteristic function of the random variable or the random vector x. Now in this case, instead of going back to the original probability measure mu, which is essentially p compose x inverse, we will just use the notation phi subscript x just to denote it is essentially connected with this characteristic function of the random vector x. So this is the notation that will be used when I am doing the discussion involving any random variable or a random vector. Now we first list some characteristic functions of standard random variables. Alright. So these are all standard computations which you can verify, and I am sure all these statements you have seen in your basic probability theory. So this is essentially a recall. So we are saying that if x is degenerate at some point c on the real line, then the characteristic function exactly has this form, that is exponential iuc, and this is for all u in the real line. Now if x is a binomial random variable with the parameters n being a positive integer and p is between 0 and 1, then the corresponding characteristic function has this expression for all u in R. If x is a Poisson random variable for some parameter lambda positive, then the characteristic function has this form. Here u again varies over the real line. So always the characteristic function is defined over the whole of R in the case of random variables over Rn in the case of n dimensional random vector. Now, let us look at another example of a discrete random variable which is given by geometric p distributions for some p between 0 and 1. So, just to clarify, here we are using this specific structure of the PMF using the number of failures interpretation, that whenever we are looking at this small x being the number of failures before I see the first success. So, here in this situation the number of failures required to see the first success can take value 0, 1 up to so on, and therefore, the corresponding probability is exactly this, and here that is how the probability mass function gets defined, and for all other possible values of small x the probability is 0, and corresponding characteristic function is exactly of this form. Alright. Now, if I move on to the examples involving continuous random variables, then let us start with the case of uniform AB random variables where A is less than B, then the characteristic function has exactly this form. So, here we have to be careful that this formula that is written here, that is applicable when u is not 0. If u is equal to 0, that takes the value 1. Alright, let us now consider this special example of a Cauchy random variable. So, here I am looking at this specific structure of the probability density function, and here the corresponding characteristic function can be computed, and this turns out to be exponential minus mod u for all possible values of u in the real line. If I look at the exponential random variables with parameter lambda positive, then let us consider this PDF, this structure of the PDF. Then here what will happen is that the expectation will turn out to be lambda. So, sometimes we will refer to this situation is that this is x is an exponential random variable with mean lambda. So, sometimes we will just state this fact just to mean this setting, alright, and in this setting the characteristic function has exactly this form, and this is again for all u in the real line. Now, let us move on to the case involving the normal distributions or the Gaussian distributions. So, if you take such a random variable with mean m and let us say the variance sigma squared, then the corresponding characteristic function has explicitly this structure for all u in the real line. In particular, if I am interested in the standard normal setting, meaning the mean is 0 and variance is 1, then the characteristic function is exactly this one, exponential minus half u squared. Alright. Now, in the higher dimensional setting, we look at one specific example of multivariate Gaussian random vectors. So, let us say in the n dimensional setting, I have the mean vector b and the variance covariance matrix k. So, then if I look at the corresponding random vector, which is a Gaussian random vector that I am looking at, here the characteristic function has this form where u is coming from Rn. So, here we have also used this transpose notation just to connect it with the usual dot product notations. Alright. So, now we have seen many examples of the characteristic functions. We are now going to focus on basic properties of such functions. So, the first one in this list is the fact that at 0, meaning at the origin, the characteristic function takes the value 1. So, here we are looking at the n dimensional setting. So, the 0 comes from Rn. So, the domain of the characteristic function is now Rn. The second fact is that phi x is bounded and continuous, and you can actually improve the continuity statement by saying that it is actually uniformly continuous. So, let us see the proof of these facts one by one. Now, you see that for notational convenience, we are now going to discuss the proof in dimension 1 only, but using the appropriate notational changes, the general n dimensional case will follow, and that is just using the similar lines of argument. So, just for simplicity, we are just focusing on dimension 1 to explain the ideas. So, let us look at the case of a random variable x now in one dimension, and we consider the corresponding law and we write it as mu. So, here the characteristic function therefore is the integration of this quantity. So, here we are looking at exponential I times 0 times x, that just turns out to be exponential 0 in the integrand, but exponential 0 is nothing but 1. So, therefore, we are just integrating the constant function 1, which is giving us the measure of the whole real line, but mu is actually a probability measure on the real line, and therefore, the integration value must be 1. So, this tells you that the characteristic function at the origin takes the value 1. Now, we move on to check the boundedness of the characteristic function. So, here if I look at the modulus of the characteristic function, first I can push the modulus inside in these calculations, and here note that modulus of exponential IUX, that is always 1. So, again we just end up with the measure of the real line, which is 1. So, the characteristic function is actually bounded by this constant 1, alright, but note that characteristic function is a complex valued quantity, and we are saying that for all possible values of u coming now from the real line, the modulus value is exactly less or equal to 1. So, let us now check the continuity properties. So, here we are going to discuss the continuity properties or verify the continuity properties by the sequential criterion. To do this, what we do is that we first fix a u in the real line and choose some sequence un of real numbers such that the limit of un is exactly u. Then if I look at for every fixed value of n, I look at the un, and exponential I un x has this split in terms of real and imaginary parts. But now if I let n go to infinity and keeping small x fixed, I will just land up into this by the continuity of the real part as well as the imaginary part, and that is exactly exponential I u x, and this is true for all fixed x in the real line. So, therefore, we are having a pointwise convergence happening here, and just observing the boundedness that we discussed earlier, and we will just refer to the dominated convergence theorem, or essentially the bounded convergence theorem, because we are using a probability measure in all of our computations. We will conclude that the limit of phi x of un is exactly this limit, just putting the definition in, but this limit can be pushed inside just by using the dominated convergence theorem. If you are unclear about the exchange of limit and integration, all I suggest is that you split this integration into the real part plus the imaginary part and appeal to the dominated convergence theorem separately. You will end up with exactly this expression. So, please ensure that you understand this step, but that last expression is exactly the characteristic function of x at the point u, and therefore, we have managed to show the relevant sequential criteria for continuity, and hence phi x turns out to be continuous. So, here it is important that we have first proved the boundedness, and using the boundedness ideas we have appealed to the dominated convergence theorem together with this underlying probability measure to get the relevant continuity. Now, what we are going to see is that this continuity statement that we have proved for each point u separately can be improved to the uniform continuity statement. So, let us see the proof. So, here what we do is that we observe that for any two real numbers u and v, if we look at the modulus of the difference between phi x of u minus phi x of v, then that is turns out to be dominated by this quantity. But now I can take exponential I v x common from this expression, but then the modulus of exponential I v x is always equal to 1. So, that essentially leads us to this expression, but you see that here the last expression that we have obtained, the integrand here purely depends on u minus v and not explicitly on the values of u and v separately. So, this depends on u and v only through the difference. So, therefore, if I want to check the uniform continuity, all I have to apply is that this integrand here essentially is continuous at 0 and the value at 0 is exactly 1. So, just use that, observe that and complete the argument. So, please check this is left as an exercise for you to complete the argument, alright. So, therefore, the characteristic function of any random variable or a random vector actually is a uniformly continuous function, and it is also a bounded function. Now, I leave you another important exercise. This is very useful in computations, that if you have a n dimensional random vector, then I can appeal to certain change of variables or a linear change of variables through a matrix which is, let us say, m by n dimensional, and let us say A is a vector in Rm. Then if I look at the vector A capital X plus small a, then this will give you a new random vector, but now this will be now m dimensional. Now, for this m dimensional random vector, we are interested in computing the characteristic function. This can be computed in terms of the characteristic function of x by multiplying this constant here for every fixed u in Rm and looking at this quantity here. So, that gives you change of scaling using this matrix A as well as the shifting of origin by this vector small a. So, this is how under linear transformation the characteristic function changes. We now look at another important property of characteristic functions involving smoothness. So far we have only ensured that the characteristic function is continuous. We have in fact shown it to be uniformly continuous. Now what we are going to show is that with additional conditions on the random vector or the random variable x, we can in fact have derivatives of the characteristic function. So these discussions that we are going to do will be in the random variable setting, but again for the case of random vectors similar statements can be proved very easily. So in the case of random variables we are talking about derivatives of the characteristic functions. Whenever we are going to go to the setting of random vectors, we would look at partial derivatives of the characteristic function. So let us see the results involving derivatives of characteristic function. So we start with this setting that we have a random variable with law mu. Now suppose that we have expected value of mod x is finite, meaning x is actually in L1. Now here we are going to claim that under this assumption the characteristic function must be once continuously differentiable, meaning I must have the derivative of the characteristic function which exists for all u, and moreover the derivative should be continuous in the variable u, and moreover we actually have a important expression for this derivative given by this integral formulation, which can be understood to be this specific type of a expectation of a function involving capital X. So let us see the proof. So here to do the proof, all I have to ensure is to look at this kind of expressions as small h goes to 0. So first look at for every fixed h non-zero, this expression can be written from the definition that I take this part common outside and then I am just left with this part inside the integration. Now here let us focus on the integrand. So here this modulus value of the integrand here can be shown to be dominated from above by mod x. Please check this, that this holds for all values of u as well as small x. Now if you look at it separately in terms of the real part as well as the imaginary part, then the real part of the integrand, the modulus of it is dominated from above by the modulus of the actual complex number, and that actually is therefore dominated from above by this number, and hence we can appeal to this bound when I am looking at this integration. So if I just use this bound here, I just look at the fact that this is actually coming back to the expectation of mod x. Why? So let us write down the change of variables using measure theoretic integration. So as per definition, this is mod of x of omega integration with respect to the underlying probability measure, and this is happening over the domain side. But if I change variables, I will end up with mod x here. The integration will now be over the real line, but the measure will now be p compose x inverse with dx coming here. So that is just the change of measure that is happening here, and this is exactly the expression that you have obtained because the law is exactly mu. So therefore we ended up with expected value of mod x, which we have assumed to be finite. So therefore we have the integrability of the modulus of the real part. Similarly, if I look at the imaginary part and the modulus of it, that is again integrable with respect to this probability measure mu, that is again upper bounded by expected mod x. So here we can now appeal to the dominated convergence theorem because of this integrability conditions, that we look at the real part and imaginary part separately corresponding to this limit appearing here. So we want to show that this limit exists because I want to establish the existence of the derivative of the characteristic function. So here u is any real number and I am just varying h as h goes to 0. So now I can push the limit inside the integration. So I am just appealing to the definition of characteristic functions here. So this exchange of limit and integration is by the dominated convergence theorem. But now as soon as the limit is passed inside the integrand, I just end up with this expression at the end in the limiting sense, alright, and that is what we have claimed as part of the theorem. So this is the expression that exists as per our assumptions, and therefore we ended up with the existence of the derivative, and moreover we have obtained this specific expression in terms of an integration involving the underlying probability measure. Now here we want to show also that the derivative of the characteristic function is continuous, but again we can appeal to the sequential criterion and use the dominated convergence theorem arguments that we have discussed earlier while proving the continuity of the characteristic functions. So again what we will do, we will appeal to the sequential criteria of continuity, that if I take any real number u and I will approximate the u by a sequence of real numbers un, then I will look at phi prime at un. I want to show that that is converging to phi prime of u as n goes to infinity. But to do that, I have the explicit expression of phi prime of un in terms of these integrations. I will just pass to the limit and the limit will go inside the integration and that will give us the corresponding expressions. So please work this out. This is exactly similar argument as discussed earlier. Alright. So here in this theorem what we have looked at was the first order integrability, meaning x was in L1 of p and there we had the first order derivative of the characteristic function. But we can repeat this argument by assuming that the kth absolute moment for some positive integer k exists. Then by a similar argument we can look at the fact that the characteristic function has derivatives of order up to k, with each nth order derivative being given by this expression, and moreover the highest order derivative is continuous. So we can follow a similar argument using the dominated convergence theorem and we can establish this fact. But moreover what we can actually obtain specifically under this setting, that if I assume that the kth order integrability for the random variable x is there, then in particular all moments of order n from 1 to k exist, and therefore we can link the moments and the derivatives of the characteristic function at 0 by this relation, that the evaluation of the nth derivative of the characteristic function is exactly I to the power n multiplied by the nth moment of x. So here n varies from 1 to k. So under this assumption of integrability, the kth order integrability, I will end up with the connection between the moment and the nth derivative of the characteristic function. But here I would like to make an important note that there are explicit situations where expected value of mod x may be infinity. For example, we can go back to the example Roman 6 as part of example 5. So here x is a Cauchy random variable as discussed there. So we have expected value of mod x is actually infinity in this situation, and here recall that we have mentioned that the characteristic function is explicitly exponential minus mod u for all u. Now here you can check that this is not differentiable at 0. So again we have discussed in the theorem that as long as the first absolute moment is finite, we can talk about the derivatives. So here we have seen a completely opposite situation. When the first absolute moment is infinite, in that situation the differentiability may not hold, and here it is not holding at the value 0. And finally, once we have identified the derivatives of characteristic functions under these assumptions of integrability of x, as an applications of Taylor theorem, we can expand the characteristic function near 0 like this, and here this is, since this is just a standard application of the Taylor's theorem, we skip the proof. So this you can immediately get by Taylor's theorem. So the assumption is, again, for some positive integer k, let us say a random variable has the kth absolute moment of x is finite, then I can expand the characteristic function as a finite sum involving some error like this. So here the error is of the order small o of mod t to the k as t goes to 0. So what does it mean by small o? It simply means that the characteristic function subtract the finite sum as written there and divide by mod t to the power k. Then this ratio will go to 0 as t goes to 0. So this is the meaning of the small o notation. So please get used to this. Again, the idea is, as long as you have the first kth order derivatives, then you can have the, first of all, the links between derivatives of characteristic function at 0 and the moments of the random variable, and also you can link the characteristic function together with this finite sum, and the error is of this order as t goes to 0. This is in terms of the small o notation. Alright. So, in this lecture we have looked at characteristic functions definition and we have also discussed some very basic properties. Now, in the next lecture we are going to look at the recovery of the underlying probability measure. Remember, starting with a probability measure we have discussed the definition of a characteristic function. Now, what we are going to do is that we are going to start off with some unknown probability measure, but with explicit characteristic functions, and we would like to recover the probability measure from there. So, this is what we are going to discuss in the next lecture. Thank you.